Okay, so first day of classes, I mentioned there are two types of statistics, frequency statistics and Bayesian statistics. In a way, both of them are sort of related. As I said, in advanced Bayesian statistics course, typically we can associate Bayesian statistics directly to frequency statistics. So what does this mean? This simply means we are going to change or change the probability of an event based on new evidence. Typically, we make an assumption when we collect data, we want a simple random sample, we don't want any bias, a whole bunch of stuff when we collect data in frequency statistics. In Bayesian statistics, we do the same, we collect the data, but once new evidence comes into play, we've got to update what we have. Now, this has a lot of applications in machine learning and so forth, but I will show the relationship between Bayesian and frequencies later. Bayesian statistics goes back to something very, very important. Conditional probabilities. And a conditional probability is a probability. By all means, all probabilities are conditional. We just don't write it that way, but everything is based on a condition. So what does this mean? So we all know that. What is that equal to? And when we do that, what happens? Multiply the probability of A by probability of B. Did you run the same mask last time?
Yes.
Not you, him, Peter.
Oh.
Because that's one of our favorite colors, turquoise. I'm surprised that I didn't notice it, last time, because it always catches my eye. So probability of A intersect B is simply the probability of A multiplied by the probability of B. We know that, but this can only happen if A and B are independent. Going back to maybe the first day of class, maybe the second, we said this is related to the concept of replacement as with replacement in terms of sampling. So if we do it with replacement, we end up getting a simple random sample and the events are independent. Suppose A depends on B. Then the probability of A intersect B, it is, a bunch of events. Multiplication law or the fundamental rule of counting still says the same thing, that you've got to multiply a bunch of probabilities or the number of ways they all happen together. And we're going to use the same thing, but I'm going to make an assumption that suppose A depends on B and A occurs first. So I am doing it this way so that you can understand the definition of conditional probability. But in practice, this need not be the case. In other words, we don't have to have events occurring in a sequence. So I will mention that once I write the definition. So A occurs first, so this would simply be probability of A. But B depends on A. Do you agree?
Yeah.
So we have the probability of B. We put a vertical dash. That vertical dash means given. And that is B given A. If I solve for B given A, or probability of B given A, that would equal to the probability of A intersects B divided by the probability of A. Good so far? Yes?
No, wait, okay. So if A depends on B, but it's B given A, why, or is B given I?
B depends on A. Oh, I'm sorry.
I was like, what?
Oh yeah, B depends on A. Thank you.
Oh, thank you. I was like,
Yeah, I'm sorry. B depends on A.
depends on what I think.
My brain is going ahead of me. B depends on A.
Thank you.
He was freaking out. Thank you.
I was,
Or else all of Bayesian statistics would be like astrology.
it feels like it.
Junk.
Oh
I can't believe even today people believe that stuff.
yeah. Bro, you must be a cancer. You're not sure.
What did you say?
Bro, you must be a cancer. You're like, you must be.
I am a cancer.
I don't know.
But still, it is a junk.
I said you were doing stuff. It's not a prediction. I think I'm just like.
Now I could make a statistical observation. You brought that up, so there is a good likelihood that you are a cancer.
No, I'm a Leo.
Done. Okay. See, junk.
Powerful.
A depends on B, and B occurs first. Finally, I got that right. So here, B depends on A, so probability of A intersect B is probability of A multiplied by probability of B, given that A had already occurred. Over here, A depends on B, so probability of A intersect B, B occurs first, so probability of B, and A depends on B. That would be the conditional probability of A given B. If I solve for it, that's what I will have. So this is the conditional probability of B given A. That is the conditional probability of A given B. A key thing to note, or an important remark. In terms of inference, probability of A given B is not equal to probability of B given A. Question, Dennis. 1. So Dennis says 1. Why? You can't use math. You know, you can't use the formula. Oh. It's like, oh. Without using the formula. Forgot it. Jack? Huh? Andrew, go ahead.
So it's given A, you're saying given A. So A has already occurred. So the probability of A having occurred, well, it's already occurred. Or I suppose if it's A occurring again, then it's just the probability of A.
Okay. What is your answer?
Well, I was saying again, because it's A given A, so you've already said, like it's pretty much said, you already established that event A occurred. So the probability of A given that A occurred is 1 because it occurred.
Okay. Hold that thought. So probability of B given B would also be 1. Now you guys said, oh, B occurred already, A occurred already because of this definition. When I started this, I said, I'm writing it this way so that you can understand the formula. Do you remember? How do we interpret it in a practical sense, or how do we interpret this in Bayesian statistics? This is considered as new evidence. Okay, so new evidence toward A. Don't consider it as an event. So whatever I wrote here, whatever I wrote there, those are undergraduate ways of learning conditional probability. And it is easier to come up with that formula if I wrote it this way. Does that make sense? But in terms of interpretation, in terms of Bayesian statistics, all we are saying is that A is new evidence. In other words, I can find the probability of B directly, but what would happen if and B depends on A, and what would happen if I brought in some new evidence that will affect B, right? At that time, the probability could either go up, go down, or remain the same. Do you agree? So you can observe something and come up with a probability, and then you can bring in new evidence that will affect B, then it could either go up, down, or remain the same. So you have adjusted the probability of B by bringing in new evidence. That makes sense. So, which is one of the reasons Bayesian statistics a bit more, reliable in certain fields such as medicine, because oftentimes we get new information and we have to update stuff. In medicine and legal studies, it is quite useful because we can constantly update based on new evidence. Are we clear? Okay, so that said, here is a question. Is A given B or B given A an event? As in the definition of an event. We've defined event at the very first day of class in terms of set theory. I would like to know if A given B or B given A is an event in its entirety. According to this, A, B could be an event if it happens in sequence. Let's say you've got a box of candy and you have a bunch of candy in there identically wrapped. You have 5 Butterfinger bars, 5 Skittles, and 5 Kit Kat, right? Identical because you don't know what you're picking. Now, let's say I love candy, so I put my hand in, grab, so 5 Butterfinger, 5 Kit Kat, what was the other one? Skittles. I put my hand in, and I would like to know the probability that whatever I picked is Butterfinger. 5 out of 50, which would be 1/5, 20%. Done. 1/3, bad math. 0.3333. Right, that is 3.33%. And I ate it, but I want more candy. So I shuffle the box again, and so that's the first time. No, second time. So what is that probability? I would like to Butterfinger this time, Skittles this time.
Okay. The was 5 out of, well, it's 14.
5 out of 14.
One last Skittle, or one last Butterfinger.
Right, because I took one candy out. So I ate the Skittles, and then still not satisfied, I shuffle the box and grab one at random. What is the probability that I don't pick Kit Kat? It could either be Butterfinger or it could be Skittles. 9. Already took a Butterfinger out, already took a Skittles out. So out of 10, I took 2, so it's 8 out of 15. Not 15, 13. Right. So when I do it in sequence, this depends on that. Yes. That depends on that. Correct. So this is what we call without replacement. We know that. This, suits well with that definition, which we use primarily to derive the formula. Now that I've given you this bit, A is considered to be new evidence that we present or bring into the equation to see if the probability of B has changed or not, or if it remains the same. That said, based on the proper way of seeing a conditional probability, would you consider A given B or B given A as an event? Do you follow my?
I would say no, maybe it's a situation that involves event, but I think it's not a specific event.
Okay, well,
Yes.
Matthias says no. Then what was your answer?
Because the events are A or B. So A given B is the situation involving them, but it's not per se one event.
Okay. Any other answers?
Well, I mean, there is an event, it's event A, it's just event B happened before.
Yeah, but it's like a sequence of events that, it's not like you're gonna do a pooling from the box and that A given B will come out, you have to do two poolings. So
Every event is a subset of the universe of the omega, but it medium and subset. Which is,
You say yes to Joe, what?
Because it doesn't make a subset, even like, it just could be that A has to come from more than that intersection. Still, yes, I don't know.
Any other answer?
I don't think it is because it has to be a subset of omega, it has to be, every element has to be a subset, be a part of omega. I don't think E given A is a part of omega.
Okay, so it's giving in the situation
I don't know.
that is, quite related to theoretical explanation, but I'm going to say no. If you want to stick to this definition, once again, I use that and I use that statement, and I showed you this example just to get at that formula, right? And this wasn't there. And now, later on, I mentioned, well, A is just new evidence that we bring into the situation so that we can observe the probability of B, correct? So what does that mean? Got your name, Joe? No, Joe. Is that?
Me?
Yeah.
Christopher.
Christopher.
Okay.
Christopher said, something related to a sample space and something like
Yeah,
that.
so
I got half of what he said.
I got half of what I remember.
Okay, great. We're in agreement then. So, in this scenario, both events belong to the sample space. Do we agree? Because the entire thing would form a sample space.
Yeah.
But here is a condition that I simply say, okay, what is the probability of me picking a Butterfinger bar, given that, let's see, given that you cut your finger as you put your hand inside the box?
What?
Huh?
I pull my hand out.
Oh,
Who said that? He's gonna, what's your name? Nick. Nick says, I'll pull my hand out. We're about to say something.
Well, I was gonna say,
pretty tenacious.
I guess it would be the same, it's not very different.
Okay, what else? I'm using a very trivial,
It's a
silly
really
example.
weird
Pay close attention, so I'm going to stick my hand in. I'm trying to find the probability that I get Butterfinger, right? But I'm presenting new evidence to you that as I went in trying to get that Butterfinger, something cut my hand. Excuse me, not hand, finger. Let's say brandy, boom. Right? What do you think the probability would be? Zero. What's your name? I forgot your name already. Nick, zero. So Nick says zero. Okay, what's that? So according to Nick, the probability changed. Who else? Andrew said.
I said the probability wouldn't change, that's the.
Wouldn't change. That was Andrew. Anything else? Anyone else?
Question actually you asked, that's the question.
What?
Depends on how willing you are to still try to grab it after you cut yourself. Like, are you still gonna go for it?
Okay.
Is it independent or not?
It's clearly dependent. So we are talking about dependency.
Well,
Right.
you're really tough. I would assume I still go for it.
Yeah, I understand that the only option is either you just don't, the event doesn't happen at all, or the event happens, but the probability of it happening doesn't change because you still might grab the same thing.
Right? So you see all of these options that came out. So the gremlin cuts my finger, I feel the pain, and I immediately go like this, and I say, I don't want the candy at all. I'm angry. I have to go fix this, right? Or I stick my hand inside the box. Gremlin cuts my finger. Oh, why not? You know, I can take this. So I grab that butterfinger, get it out, you know, open the wrapper, and I eat this bar that's mixed with my blood, and I enjoy it.
Some people might do that.
Right? Exactly. That's a possibility. Huh? Good answer there. But still, if you're grabbing the gremlin, then the probability of you grabbing Butterfinger would be 0. Right? So, in all cases, I used something that didn't even, you know, play a part here in the sample space. I'm just bringing in something which is merely evidence. It's coming from somewhere, but that evidence seems to have an effect on B, right? If we extend it really, if we take it further and we said every single possibility that I can think of that could come into play here to affect B. In other words, I define millions of sample spaces or billions or more than that, and account for every single possibility for A to be an evidence, bring it to B, then that would be an event. But we can't go that far, right? So it's coming from somewhere else. So it's just evidence that comes into play and it affects the probability of B. So at the end of the day, the event of interest is always B. So here, A and B are the events. I should put A over here and the B over there are the events. The one after the vertical bar simply indicates that it is new evidence. Does that make sense? Because of all this interpretation and stuff, Bayesian statistics always requires extra care when you're trying to write something or write an article, etc. So the problem is there are two boxes behind a closed door, and one is blue, the other is red. There are 5 cards numbered 1 through 5 in each box, and the color of the card matches the color of the box. So 5 red cards in the red box, 5 blue cards in the blue box. They're all numbered 1, 2, 3, 4, 5. There is a wizard behind the door. He picks, he pulls 3 cards at random from either of the boxes. So it could be red, it could be blue. He's going to do it without replacement. And after he pulls out 1 card, he's going to yell out a number, one at a time, 1, 2, 3. And you're outside the door and you're going to write the numbers in order, in the order that you hear. So assuming you're not deaf, assuming that you understand what ordering means, those are all evident, right? I can add those in and that's going to affect the probability. You see where I'm going? So note it is without replacement. The question is, what are the chances that I will get 1, 2, 3? How many cards do I have in total? 10. The color doesn't matter to me, right? So first time I have 10. And how many possibilities would I have to pick that up?
2. There are 2 ones.
2 ones. And the second, I picked 1 card out, I'm not replacing it back. So how many options does the wizard have? 9.
Yeah, oh, for the wizard,
And he picked 2 out, so the 2 ones came out. So how many 2s do we have?
you pick one out, you pick one out. One,
Yeah, he picked 1 out, but how many 2s do we have? 2.
Yeah.
Thank you. Next dog, you have 8. There is a 1, there is a 2, and we just want 3s. There are 2 3s. He's going to pick 1 of those. So 2. So 2 times 2, 8 and 8 would get cancelled. So the probability is 1/90. Good. So we're going to find the same probability, but this time there is a sneaky witch, and she informs you that all cards are blue. Which she kind of knows everything. Even though the wizard is going to read 1 at a time, the witch can read the mind of the wizard, and the witch is going to inform, right? Somehow she's coming up with this evidence that would fit the problem. How about that? So I want you to give this problem a try. Clearly, would you agree that you get some new evidence for the exact same event? Yes? The event here is getting 1, 2, 3. All I brought in here is evidence, not necessarily an event, but evidence, because which has nothing to do with the problem. But I'm bringing in new evidence. Now that I'm bringing in new evidence, how would that probability change? The hint is you have to use conditional probability, define, A, B, and use the formula and see if you can get the correct answer. Good, guys are getting it. Who's planning on going for higher education like MS, PhD? Are you guys interested in biostatistics? No. Maybe after this you will. Or I just scare you away from statistics altogether. So this is an easy problem. So I'm going to define B to be the event that you write down. 1, 2, 3. Right. And A is the information you collect from the sneaky witch. Right. I'm going to use the formula. Where did I put? Oh, it's right here. So we want to find probability of B given A. So that is the probability of A and B divided by the probability of B. Yes. Casey asked me, well, we have this probability, and how do we know this is permutation, combination? Most of you, drew those dots, dot line, which is a good thing. But the purpose of permutation, combination, and the different cases that we did is to understand the number of possible ways, because at the end of the day, probability is dependent on the count, of possibilities that we have. So combinations, permutations, and its types, and their types are simply ways to get the number of ways so that we can compute the probability. So probability of B should simply mean you're writing down 1, 2, 3. Yes. Now, what is the probability of you writing down 1, 2, 3? 1 over 90. So how did we get that 1 over 90? What is it?
Second simple formula, probability of A at the bottom.
Exactly. Thank you. It doesn't make sense.
It makes sense to me.
Because in my head, so information from the sneaky witch that is the evidence or denominator A. Again, my mind is going ahead of me because I'm thinking of the next problem, A and B. So what is probability of A? The information or the evidence that I'm getting is that all of them are the. So 50.
Oh, no, it would be, because it's, yeah, that would make sense. Because it's, that makes more sense. First one is 50 and a half of that.
How many ways could that happen? We don't want the probability, I just want to know the number of possible ways in which it could happen. So cardinality of A. How? 60. How did you get 60?
The 5, the permutation, 5, 2, 3.
Right, we order matters and it's done without replacement. So we are trying to find permutation. So that would simply be 5P3. Yes. And the probability of A is you're picking 3 cards or that would match 1, 2, 3. So we want to write that probability. It would simply be 1 over 5P3. So I'm going to put the cardinality as 1 over, just be 5P3, the number of possible ways in which it could happen. Not probability, it's just the cardinality.
That comes from you simplifying.
Yes, it comes from simplifying, but I'm trying to show something else. Now, the probability of A intersect B, and what is the cardinality of A intersect B? A is the information from the sneaky witch that all cards are blue. B, you write down 1, 2, 3. In other words, the wizard is picking a card from the blue boards. And the first card has to be 1, second card has to be 1, third card has to be 1. So from 1, you are choosing 1. Would you agree? There is only 1, and you're choosing 1. And there is only 1, 2, and I'm choosing that 2.
One blue, blues.
In the blue box, right? Because it's all blue. And lastly, I have 1, 3, that's blue, so that 3, I'm choosing 1. In terms of cardinality, it would be 1 times 1 times 1, 1 over 5 being 3, that would be 3 times 4 times 5. Yes? That should equal to 1 over 60. The way you guys did, which is perfectly fine. All I'm trying to do here is to make a connection between the counting approach, where you have the number of ways, and finding the probability. We could have done the exact same thing with the probability directly, but there will be a denominator term there, they will get cancelled, you will end up getting the same answer. If you take the other approach of drawing those lines, so we know all cards are blue, so you have 5 in total in the blue box. How many of them favor 1? There is only 1 card, so 1 over 5. Now that the wizard had picked that card out, and it is without replacement, we would have 4 cards left. And how many of them are 2? Just 1. Without replacement, and then I have 3. Pick 1, so it's 1 out of 3. So 1 over 60. Yes.
Write the fraction method, or do you want us to write the other?
Either would work for me. As long as you explain and as long as I understand that you understand, we're all good. Once again, want to make something clear that on an exam, I want to know if you understood. You know, if I can see that you're understanding stuff, but you're making mistakes here and there, that's okay. I'll still give you partial credit. But if you just threw a number, you know, 1 over 6, 1 over 60, yeah, it is correct, but how did you get that? Right, you could have guessed it. So I'll just give you 2 points out of 10. But if you just put 1 over 3, that's a wrong answer completely, and there is no explanation whatsoever, that would be 0. Right? So I would like to know that you understand the process, because that is useful.
And so that's our part B, we can solve basically as the only.
What is the difference between part A and part B? Of course, the answer is different.
Like the arithmetic difference?
Huh?
The arithmetic difference? Or
Yeah,
the-
what happens to whatever we compute?
Oh, so not the arithmetic. Okay. You add.
What happened to the probability? Let me be more clear.
It got smaller.
Did what?
It got smaller.
It got smaller. It grew.
Bigger. So
More likely.
It's like the third, 1/3 burger and the 1/4 burger. Right? So 1 over 60 is definitely bigger, right? So we're dividing it by a smaller number. So 1 over 6, what is that? 0.0167. Yes.
Correct.
And 1 over 90 is 0.0108.
0.01 repeating.
Yes.
Oh, 1 repeating, okay, we're close. So the first one is about 1% chance, the second one about 1.67% chance. So it went up. Now, I want you to tell me, does it make sense from a practical standpoint? You all got the math part right. But from a practical standpoint, does it make sense to you?
Because
Why is that, Dennis?
Because you're removing all cases where any number of the cards are red. So even though you're removing a few of the potential successes where either 1, 2, 3, or any combination of the like are red, you're removing even more, I guess you call failing cases, where you have a different set of numbers where one of them is red. So because you're removing more failures than you are successes, the probability is going up as well.
Okay, someone else, but I had to have that.
Like,
Was it
possible to draw one.
You?
If you draw one, I just good.
You're okay? Okay, so in a sense, you're bringing in new evidence into in finding the probability. In this case, the probability went up. Let's say you were sitting outside a grocery store and you see a person who walks inside and is wearing a turquoise sweater, right? And walks inside the grocery store. In your mind, you have a feeling that this person is going inside to buy a hygiene product of some sort. Your friend who went to get coffee comes back and he asks, you know, what is the person going inside the store to buy? And you say, oh, the person went in to buy a hygiene product. So the person calculates probability, the friend who came to the coffee shop comes up with an answer. So that's the first answer, that's part A. Now, having observed, I'm going to give my friend additional information. I'm going to tell that person that the individual is female. Right? Would that change the probability? Absolutely. So bringing in new evidence will change the probability, but not necessarily going up. It could also go down, or it could remain the same. Does that make sense? Okay, so we are clear with this.
Like 110 times 1.
Okay, so probability of A given B. So here we're going to treat B as evidence in the sense you're telling that we have 1, 2, 3. Given that information, what are the chances we would have blue cards? So this would be the probability of A and B divided by the probability of B. So we want all of them to be blue cards, and we need to get 1, 2, 3, right? So what is the probability that what is the probability you pick a 1 and it is a blue card? 1/10, right? Because you have 10 cards in total. One of them is the one that's coming from blue. So it's 1/10. 1 is blue and we have to get to 2. That would equal to 2 over 8. No. 1 over 9. Right? And then the next one would be 1 over 8. Yes? The denominator is probability of B, which is the probability that we get 1, 2, 3. Right? And what is that? I think we found that already over here. Yes? Did we not?
No.
Oh, that's big given A. What is the probability?
Over 9.
Oh, 1 over 90.
Look what that results in.
That's 1 over 8. Okay.
Well,
It makes sense. What's the name? Shay, you're because I was trying to get to this. Okay, it makes sense. Does we have 1 over 8?
It's not, the chances of both having, what's the chance of one having given that you know you're going to roll.
In terms of counting, if you want to write it in terms of counting each of them, how would you write it? Because we want to use a counting principle. Now, some of you didn't even take this approach, went directly using logic and were that's going to break. That's the fun. I took this approach because some problems writing it out this way helps. So, in terms of counting, how can I write the numerator? Like I did up there. 1 choose 1, 1 choose 1, 1 choose 1, divided by 10p3, because ordering matters. If I'm just selecting a bunch of them, it'll be 10 choose 3. Does that make sense? The denominator, you could take either approach like we did in the first one, or here, and you will get 1/8. Does that make sense? Some of you did it directly, using logic, that's fine. But I want you to use this because it's so close, so far. Probability A intersect B over probability of B, because this particular formula can be expanded to multiple events. So later on, I'm going to write an expression for probability of A1 intersect A2 intersect A3, where let's say A1 is the weather today, A2 was the weather yesterday, and A3 is the weather tomorrow. I have to condition the weather tomorrow on A1 and A2. Does that make sense? And if someone came and asked you if yesterday it was raining, today it was raining, and what is the probability that tomorrow is also raining, that would require a chain of, the conditional probabilities, because each day is dependent on the previous one. Does that make sense? Which is why understanding this formula is very crucial. Good. So the point I made earlier, the probability of A given B is not the same as probability of B given A, makes sense. Yes? Okay. So we should always keep in mind that conditional probability is in fact a probability. We shouldn't forget that aspect. So probability has a bunch of properties, and every single property that a regular probability will satisfy will also be satisfied by conditional probability. What do I mean by that? We all know zero less than or equal to the probability of A less than or equal to 1. Yes, that is something we know. Certain event, impossible event, probable event, so forth. Let's say new evidence is E. Right? So we can write this as probability of A given E is also less than or equal to 1. But you do have to keep in mind that A given E as a whole is not an event. All we are trying to do is bring in evidence E so that we can calculate the probability of A. With me? That is the key part that you have to keep in mind. It's very, very important in Bayesian statistics. So we don't consider this entire thing as an event. All we are saying is that when I bring this evidence in, how does the probability of A change? Good? Okay. So this is simply the probability of the null set. That's the probability of the entire sample space. Yes.
So for that second thing you wrote to be true, A couldn't be mutually exclusive, right?
You are looking at them as evidence. Excuse me, as events. So,
Oh, sorry, so it couldn't be, I'm sorry.
right, think of this way, you know, the gremlin and the finger, there are multiple possibilities, and we could hit 0 by bringing in that new evidence. Now, if you think E as an event, then the only time it would become 0 is if they are mutually exclusive. So don't make that mistake. That is not an event. An entire thing is not an event. We are bringing in new evidence to see how the probability of A changes. The A is the event. We know the complementary rule, which is what? You hear that sound and all the silence? That's my heartbreak. I'm going to write it the other way around. It doesn't matter that one. New evidence is A. So whatever applies for A should also apply when I bring in that new evidence. So this would be equal to 1 minus PR of A complement given E. Oh, no. We know the probability of A1 union A2. Simplest sense would be probability of A1 plus the probability of A2 and what comes next? Minus. A1 intersect A2. Yes? Now, what would happen if we have new evidence in our condition? In other words, I'd like to find probability of A1 union A2 given E.
Would you just put the given E for each of kind of your 3 parts after that?
That is correct. And in all 3 circumstances, we are not saying that this becomes a new event, that becomes a new event, that becomes a new event. All we are saying is that we brought in new evidence. How did this change? How did that change? How did that change? So you get a new probability. So how did this change A1 union A2 by bringing in new evidence? Are we clear?
Yeah.
If you understand bringing in evidence part and not confused with the concept of events, you're good. Okay, that's a good place to stop.